When deriving pi, we can start by trying to find the area of different polygons inside of the unit circle. For example, we can start with the triangle because it is the polygon with the least number of sides. To find the area of a triangle inside the unit circle, we need to first start with the theorem to find the area of a triangle. To find the area of a triangle, we start with this area equals 1/2 base times height. But in general, if we're trying to find a case for all the polygons inside of a unit circle, we can start by triangulating the polygon, which you can start by drawing a small circle up the center inside of the unit circle, and you branch out to make small triangles of the polygon inside of the unit circle. We can then go by dividing 360 divided by 3 different triangles, and that gives us 120 degrees. Then we can proceed to trying to find the other 2 angles of the triangle. And since this is an isosceles triangle, we know that it should be 180 minus 120 divided by 2, which will give us 30 on both sides. But first, we need to calculate for the height of the triangle. And we can go and draw that in, which will split this angle in half. We can give the base a different variable for now. Let's just call it P. And we'll give the height H. So the base should equal the sine of this angle times 2. Because if we just did the sine of 60 right here, we would just get the area of this right triangle. But since we want the area of this whole section, we want to do 2 times the sine of angle 60. And to get the height, we'll want to do the cosine of 30 degrees. And when we plug both of these variables back into our original equation, we can see that the area of this small triangle, only this small triangle, equals 1/2 times 2 sine 60 degrees times cosine of 30. But since we want to find the area of this whole triangle, we'll want to multiply that by n, which is the number of sides. And that'll work for all polygons inside the unit circle after we have triangulated them. So this will equal n times what we previously stated up here. Alright, now that we found the area of the triangle inside the unit circle, which was 1.259 units squared, we know that the area of the unit circle is going to be pi, which is estimated to be around 3.1415. And we can see that there's a big gap in between these numbers, and this is very clear when looking at a diagram, because you can see that there's a lot of empty space between the triangle and the unit circle, and that is not accounted for when only solving for the triangle. And we can see, as we add a number of sides to the polygon, that there is going to be less space in between the polygon and the circle. And if we were to keep going, we will even get to the point where there is even less and less space. And if we were to find a general equation, we could almost create a polygon with 1,000 side lengths, and there would almost be an unnoticeable difference between the area of that polygon and the unit circle. Now that we have already found the area of a triangle or a polygon with 3 sides inside the unit circle, we need to derive a generic formula that will give us the area of any polygon with n sides inscribed in the unit circle. So initially we want to start by triangulating the polygon inside the unit circle, which creates smaller triangles inside the polygon. And when doing this, we should always end up with the same amount of triangles as there are sides. And to make a general statement, with any polygon, the area should be the area of one of these triangles times however many times it appears in the larger polygon. So it should be the area of just a normal triangle, 1/2 base times height times n, which is the number of sides of the polygon. But to make a general statement, we first need to find B and H. And to find B, we can do what we did the first time with the triangle. Base is going to be this value right here, and we can once again solve it by creating a height along this lower triangle. And we know that this right here is going to be 360 degrees. And if we divide 360 degrees by n, which will give us this angle, which is equal to this angle and this angle, and we divide that once again by 2, it should give us this angle right here. And if we do the sine of this angle, it'll give us this value right here. And 2 of these will equal the base of the triangle. So to put that in other terms, B will equal 360. This angle right here will equal 360 divided by 2n. And to get one of these, to get this length right here, we do the sine of this value. And to get the whole base of the triangle, we want to do 2 times the sine, 360 divided by 2n. And the height will be given by the cosine of this value, since cosine is adjacent over hypotenuse, and since hypotenuse is 1, it'll just be the adjacent. So the cosine of 360 over 2n will give us the height. So we can plug all of these back into our original equation, and we will get something like A equals 1/2 times 2 sine 360 over 2n times cosine 360 over 2n times n. And we can go farther and simplify by canceling out this 1/2 and the 2 sine there, and the area will be broken down into sine 360 over 2n times cosine of 360 over 2n. And this formula should work for any polygon inscribed inside the unit circle. So with this equation, why it's important is because if we wanted to actually find pi, we know that the area of this unit circle is going to be pi. If we wanted to find pi, we want to create a polygon 1,000 side lengths on the polygon, and this should get us as close as possible to pi without being able to actually get the defined pi. So just like we said earlier, as we increase the number of sides on the polygon, we should get closer and closer to pi, which is the area of the unit circle. So when we plug in 3, we get 1.299, and we plug in 5, we get 2.377, 10 we get 2.939, 100 we get 3.139, and at 10,000 we get 3.142, which is very close to pi because pi is 3.14159. And since a circle is a polygon with unlimited sides, if we were to plug in infinity for n, we should get the value of pi as the area of our polygon.